Hello everyone. Today we'll be doing uniform circular motion. It is a topic in further mechanics and it's a topic which you have already done a little bit in GCSE if you have done triple. If not, still you can understand this topic. So I'm going to start from the scratch, assuming you don't know anything about it. It's a very nice topic, very simple. It has some things which we need to know. If you know them, the questions from this topic are very easy. So let's just get started. So as you can see on your screen, it is the green arrow here. The green one is showing velocity and the orangish arrow is showing the force. Now, what's the meaning of uniform circular motion? The word uniform means that the speed is not changing. So it's constantly moving with the same speed. So imagine a fan in your house which is moving at a constant speed would be doing a uniform circular motion. Earth around the sun. Okay, well, almost, not very perfect, almost circular motion, but it's uniform because the speed of Earth around the sun is not changing. Every year it takes the same time to complete this one circle. Motion of moon around the Earth, again the same circular motion, but it is uniform. Again, why is it uniform? Because the speed is constant. Okay, now here is where you stop using speed and velocity in the same breath, because if I say constant speed, fine, it's not changing the speed. It is every year, every month, it is doing the same distance. But if I say constant velocity, I can't say that. Why not? As you can see in this animation, this arrow, is it constantly changing direction? When it's at this position, it is towards the left. When it comes to this position, the arrow is towards downwards. When it comes to this position, as you would see, the arrow is towards the right. So what does this green arrow show? It shows velocity. Why is velocity changing? Because the direction of the velocity is changing, but the speed is not changing. Okay, so uniform circular motion means speed is constant and it cannot execute circular motion if velocity is also constant. That means the direction is also constant. That's not possible, because if it does not change its direction, it cannot bend and execute the circular motion. So why is velocity changing? Because direction is changing. Now, to understand circular motion in more detail, let's just understand some basic quantities that you need to know in A-level physics. First, radians. All right, let's just start from the basics. Let's say there's a body at point A and this is the radius OA. The body comes to point B. In coming from A to B, it has traveled this S, which is nothing but the linear distance. Okay, and also it has traveled this angular distance. Now, angular distance is denoted by many symbols. I am using right now here theta. So this theta, which you might have used sometimes in math, is the angular distance. Okay, now theta is angular distance, S is the linear distance. Now, as you would remember, angle is measured in degrees. Now, to relate, now if you see this entire theta here is 360 degrees. So 360 degrees. Now the standard unit for angle is radians. 360 degrees is 2 pi radians. Okay, the pi is your usual pi, 3.14 something. That's there in your calculator. So 360 degrees is 2 pi radians. That is 180 degrees, sorry, 180 degrees is pi radians. Sorry, pi radians. All right, or 90 degrees is pi over 2 radians. It's just converting degrees into radians using this relationship. 360 degrees is 2 pi radians. Now, if the radiuses are simple math, angle is equals to arc over radius. So angle theta is equals to linear displacement s over radius. Okay. Now, what you need to know from this particular slide is the angle which was measured in degrees is now measured in radians, because radians is the standard unit. And also, how do you relate angle with this s? Is angle equals to s over r. Now, what is s measured as? S is measured in meters. I don't know what I had to say, est. Like s is measured in meters. R is also measured in meters. It's a standard unit. And the standard unit for theta is radians. Sometimes, not sometimes, always you will see rad. So rad is a short form. Just like for meters you write m, you write rad for radians. Okay, now continue. Now, if again my object, which was at A, let's say the earth, has come from A to B, the speed at which this angle is changing is obviously going to be measured in radians per second. So angle over time. So this would be just like linear distance over time is linear velocity. So angular distance over time would be angular velocity. So the radians per second is the unit for angular velocity, denoted by a symbol called omega. So this is a weird symbol. You'll be using this in simple harmonic motion too. So omega, okay, I'm just going to write it here, omega. So what is omega? Omega is angular velocity defined as, I'm just writing the short form here, it is defined as rate of change of angular displacement. And what is angular displacement? Angular displacement is theta, and distance or displacement, anything would do in this case. So sorry, oops. So let's go back. Okay, so angular displacement, and what will be the unit for angular displacement? Angular displacement is theta over t. Theta is in radians, so it is measured in rad per second or radians per second. Okay, next. So obviously, if it's moving in a uniform circular motion, omega is constant. So the omega would be, let's say, 10 radians per second or 20 radians per second, but whatever it is, it would remain constant. Like for example, the angular velocity of Earth around the Sun is around 2 times 10 to the power minus 7 radians per second, and that is constant. So it is continuously moving at the same speed. Of course, it is slowing down, but not which is measurable. So for a day-to-day life things where we're not going in too much detail, we say the speed of the Earth is 2 times, it's not 2 times, it's exactly 1.99 times 10 to the power minus 7 radians per second. We don't need to know that, it's just to tell you what does the constant speed means. Now, linear and angular velocity variables. I've already explained you that if a Earth is moving from A to B, or any particle which is in circular motion about a center C is moving from, let's say, from A to B, and S is the linear distance, theta is the angular distance. We found that theta is S over R. So if I divide, S is linear distance. So if I divide both sides by t, I'm just dividing both sides by t. So this theta over t is nothing but angular velocity. I can give you the direct formulas, but some direct formulas sometimes, how many formulas your head can remember, and then also seeing the equation sheet, which formula I have to look for. If you know where it has come from, and it is not very difficult, if my angular displacement is linear distance over r, then my angular velocity is linear velocity over r. That's it. Okay, so I'm just going to write the symbols now. The symbol for angular velocity is omega is v over r. What this means is, now if I have a, let's say this one is a solid table, let me just make it here. If I have a solid table here, okay, and this, not, let's take the fan. Okay, this fan I have, which is moving at a speed of, let's say, 20 radians per second, a constant speed. Now I have different particles on this fan. The closer the particle is, the smaller its linear speed would be, but it's covering the same angle. See these two particles, this particle is farther off from the center, this particle is closer to the center. Who's traveling more linear distance? The outer particle. So as far away from the center the particle is, more would be its linear velocity. But if you come closer to the center, see all these particles, if I take A1, A2 and A3, which one, all of them have same angular velocity because they are the part of the same fan which is rotating at the same speed. But which of them would have the largest linear velocity is the particle which is farthest from the center. This is what this formula tells you. I'm just going to rearrange. So I'm going to write V equals R omega. R is the distance from the center. So larger is the distance. A1 has largest R. And then A3 has the smallest R, distance from the center, so it has smallest linear velocity. Linear velocity is dependent on the distance from the center and angular velocity. That's what this formula means. V is R omega, larger R, larger V. Okay, a question on the same formula. Let's see. What is the angular speed? So I need omega of a car wheel of diameter. So from the diameter, I can calculate radius, half. When the speed is this much, so obviously I cannot use this as my speed because the speed has to be in standard units. So I'm just multiplying it by 1000 and dividing it by 3600. Okay, I'm just doing this here and then just solving it using your calculator. So I'm just dividing it 1080 by 36. I am getting the answer as 30. So my speed is, my linear speed is 30 meters per second. And then it wants me to find omega. Omega is V over R. V is 30. R is 0.2. So I'm dividing 30 by 0.2. That would be 150. And then do not forget to write the units. This is an optional question, so you don't have to worry about that. But my answer is here. All right. So what you need to know is just how to use that equation, because you will have the equation in your equation sheet formula. All right, let's continue then. A model car moves in a circular path. All right, go ahead, pause the video and try to do it yourself. Okay. If you've done, I'm just going to do it here. So this is my radius. This is my omega. What is the displacement of point P 6 seconds after passing P? Okay, so now it's obviously, can you see meters, meters, meters? So this is, it wants the linear distance. Okay, So linear distance is speed times time. We are not using half AT square because it's moving with constant speed. Now I need to find V. V is R omega. R is 0.8. Omega is pi over 2. So this is 0.4 pi meters per second. And then I need displacement. So displacement is 0.4 pi times 6. That is 0.4 pi. Now, if it is taking, now to figure out how much distance it is actually moving, I'm going to just use my calculator to do this multiplication. Okay, so we'll just figure out this. This is coming as 2.4 pi. Okay, so 2.4 pi. Now, because it's a displacement, you need to see where the particle is. This is the distance. It's giving me total distance it has traveled. So this is not going to tell me what is the displacement. Okay, I did this so that you understand this is a common mistake you would end up doing. Now, how we see that this is moving at a speed of 0.4 pi meters per second. So how much time would it take to complete this whole circle to come back at point P? What I'm going to do this is now I'm going to calculate the time using 2 pi. We'd use angle divided by angular velocity. Okay, now what's the angle it is moving in one complete circle? One complete circle, it is 2 pi. 360 degrees is 2 pi radians, and then divide by pi over 2. So you get 4 seconds. So it takes 4 seconds to complete the circle. It starts from P, come back to point P in 4 seconds. So in 6 seconds, that is 2 more seconds, it's going to come exactly at this position. And this position, P dash, is at what distance from P? 1.6. So the displacement is 1.6 meters. You need to figure out what is it asking. If they ask you what's the distance, then this is a method you use, meters. But they're asking displacement, so you need to know where the particle is. So for that, what I did is I calculated the time it takes to complete the whole circle. I got the time as 4 seconds. In 4 seconds, it comes back to P. Another 2 seconds goes opposite to P. Displacement is the shortest distance between start and the end, 1.6. That's it. Okay. All right. So we are here to learn. We are just trying to learn, and that's why I choose these confusing questions, which the examiner reports tells that the students are likely to make mistakes. All right. Let's just move to the next question. For a particle moving in a circle with uniform speed. Now the speed is uniform. That means it's not changing. So if which is correct, okay, underline always. Sometimes it asks you not correct. So the speed is not changing, kinetic energy is not changing. That's right. Force is in the same direction. No, it is not same. I'll explain you that in a minute. Momentum is not same because momentum is mass times velocity. Momentum is a vector. Velocity changes of direction. Momentum changes because of direction. Displacement of the particle is in the direction of the force. That's not right. Displacement is in the direction of velocity. So if your velocity is in this direction, your displacement will also be in this direction. So that's also wrong. Wrong. That's the right answer. Kinetic energy is constant because speed is constant. All right, now the next thing, centripetal acceleration. Now, what is that? Sorry about that. Now, why is velocity? If you can, okay, my simple question, is velocity changing? So your answer would be yes. Who changes velocity? Go ahead, tell me. Who changes velocity? Acceleration. Yes, you're right. Acceleration changes velocity. So if my velocity is here, then in some time the velocity is here. So velocity has changed. So who is changing this velocity? The change of velocity is always caused by acceleration. So this acceleration, change of velocity over time, or in the form of differential dv over dt. But this acceleration is a special acceleration as it is capable of only changing the direction. It does not change the speed. So what does this acceleration do? Okay, point number one, only changes the direction of velocity. Oops, direction of velocity. Okay, and then second point, so it has changed the direction of the velocity but is always perpendicular to velocity. That is why it can change only direction. If it is not perpendicular to velocity, it will end up changing speed also. We don't want the speed to change. It's uniform circular motion. So now what's the direction? Okay, the direction is, so this is a center, centripetal acceleration, centripetal acceleration. So it comes here, centripetal acceleration. As you can see, every time I draw centripetal acceleration, the angle is 90. Angle is 90, 90. Okay, so centripetal acceleration, AC. I'm just using A and a subscript C. Centripetal acceleration, what does it do? It changes velocity by changing only its direction, and it is always perpendicular to velocity. Now, what we can do is I'm going to just do it here. Obviously, if there's a centripetal acceleration, if you times it by mass, it will give you centripetal force. And what's the direction? Same. The direction of the centripetal acceleration is the direction of the centripetal force. Now we need to figure out what is the direction, what is the formula for centripetal force. So if I want to find out the formula for force, how do I find out the formula for the force? Okay, so first I'm going to just go back to this. No, there's no space. Let's just do it here. Okay, what I'm doing here is I'm drawing a triangle. Okay, no, sorry, a triangle in a circle. Let's say this is a position and this is a position. Okay, so and the velocity here is this and the velocity here is this. So if I make a vector diagram for these two velocities, this is my velocity v, and then because I have to find the change in velocity, I'm inverting this arrow. Okay, I am just going to do first this, and then this is going to give me the change delta v, two vectors. Now if I take this triangle AOB, making it here, this is going to give me the displacement delta S, A, B, and O, and this is R and this is R. Okay, R is the radius. Let's just take it capital R. Now, and this is V. Now, these two triangles are similar, so delta V over V is the ratio of the sides will be same, delta S over R. Now what I'm doing is I'm dividing both the sides by T. I'm dividing by small time, delta T and delta T here. Okay, this is something you can do in maths. You can divide or multiply both the sides by the same number. Now this thing, change in velocity over time, is nothing but acceleration. So centripetal acceleration divided by v. And this here, change in displacement over time, is nothing but linear velocity over r. So I'm just taking this v this side. So my centripetal acceleration is v square over r. That's the formula for my centripetal acceleration. and when I times it by mass, I get my centripetal force, mv square over r. And don't forget, you can write v as r omega from previous slides. That's the formula. Sometimes this is asked in exam to derive this relationship. So you just have to draw two triangles showing v and delta v, r delta s, and the ratio of the sides delta v over v, ratio of the sides delta s over r is same. Divide both sides by time, and that's it. Done. Okay, pause, rewind, do it yourself, and check. Always do it the same. If you're just watching the video, not practicing, not writing, not figuring out yourself, you'll forget. The minute the video is done, you'll forget it. Okay, so do it. Now just see what's going on here. The blue arrow shows the velocity, and the black string is tied to it. As long as the string was tied, it was executing a circular motion. The minute the string goes away, the velocity, when the string breaks, what's gone? So when the string breaks, the centripetal force becomes 0. So the minute centripetal force becomes 0, there's nothing for the ball to take a turn with. So it doesn't take a turn and keeps moving straight line with that blue velocity. Speed is still there, only the speed has stopped change. Velocity has stopped changing its direction, because what has become 0? The centripetal force. Okay, let's do this question then. A mass on the end of a string is whirled around in a horizontal circle at increasing speed until the string breaks. Now this is increasing speed, so obviously it's not uniform circular motion. So once the string breaks, what path the mass takes? So we just saw in the previous animation, it would keep on moving in a straight line along a radius of the circle, a horizontal circle, a parabola in horizontal plane, or a parabola in vertical plane. What do you think? What's happening here? Now, if I would have a horizontal line, it is not going to move in a horizontal line along the radius of the circle. So that's not possible. I'll just show you with the diagram. So what it's saying is your body is here. When the string breaks, it's going to come in this direction. It's going to go in this direction. But it's also going to start falling because of the gravity. Isn't it? So what's the path followed? So this is not right. It cannot follow a circle because it's broken. A parabola in a vertical plane, not in a horizontal plane. So vertical plane, because the vertical gravity is vertical. So it'll start moving with a parabola in a vertical plane. Okay. So where does this centripetal force comes from? Let's say if there's somebody on this ride here, or somebody's on a ride here, they have to have a centripetal force. Otherwise, they will keep moving straight and they will not execute the circular path. And we don't want that. We need them to have a circular motion. We need the velocity to change. So who is providing this centripetal force? In this case, in the case of this person, the centripetal force is provided by weight, mg. Okay, let me tell you one thing. Centripetal force is not a new force. You're already the forces that you know about. One of that force would acting like a centripetal force. Like in this case, the weight is acting like the centripetal force. In the case of this car taking a turn on the circular track, the normal reaction is acting upwards, which is balanced by mg. So who's providing this necessary centripetal force? Friction. Friction is providing the centripetal force. In this case, so here we have weight, mg. Here we have friction. Here we have, it's a person holding a string, say tension. So tension is acting like centripetal force, friction is acting like centripetal force, mg is providing the centripetal force. Of course, on the earth or the sun or the satellite is a gravitational force which is acting like the centripetal force. So centripetal force is not a special force. It comes from the already existing forces. Another example, if you have a table which is moving around with some angular velocity, who's providing the necessary centripetal force to this coin if this coin is not slipping? So obviously the weight and reaction are balanced. Friction is providing the centripetal force. If the table starts moving with a huge speed, so that the friction can no longer provide that mv squared over r, they're no longer equal, so the coin would just fly off because friction can no longer provide the centripetal force to take a turn. Let's do this question. The mass remains at rest related to the turntable. That means the mass is not moving, it is at rest here. So that means the force normal reaction is balanced by the weight. And who's providing the necessary centripetal force towards the center is the friction. So what's the direction of friction is P2. Oh, isn't it? If it is not towards the center, it cannot be the centripetal force. The centripetal force is towards the center. Okay. Another kind of questions that are seen in A-level physics are on vertical circular motion. These questions expect from you that you understand what direction all the forces are acting. I am first drawing the position A. Okay, so when this black ball is here, what forces are acting? First is mg. Okay, I'm going to make a diagram here. And then the string tension, but which one should be, and the centripetal acceleration has to be towards the center. So what's the net force on the body at A? So at A, so I'm using Newton's second law. Net force is mass times acceleration, which is centripetal acceleration. What's the net force? Tension minus mg is mass times centripetal acceleration. Should we get it? Yeah? Okay. Obviously now my tension would then be mg plus mac. What is AC? V square over r. Now, at the highest position, when the string is at the highest position, somewhere here, the mg is acting downwards, tension is also acting downwards, and centripetal acceleration is also downwards. So at point B, what are the forces acting? The forces acting will be T plus mg, because obviously they both are in the same direction, so you'll add them to provide necessary centripetal force. So my tension here would be mass centripetal acceleration minus. Now my question, if this string is supposed to break, at which position it has a highest chance to break? You can pause the video and think about it. A or B, but what position the string would break if it has to break because of this circular motion? At A, clearly, because at A the tension is highest, the tension is lowest at point B, so it's not going to break at B. If it is to break, it is going to break at A. Okay, so I have an exam question exactly like that. So you're going to find out which one it is the answer by pausing it, figuring it out. If you have done that, where is it asking? Let me just do tensional string at Y is T. Okay, which one of the following equation represents the correct application of Newton's laws of motion to the ball at Y? I'm just doing it for again. So at A, Y, mg, tension, and centripetal acceleration. So T will be greater than mg. T minus mg is ma. So remember, F equals to ma, net force. A here is AC, say T minus mg mv square over r. What's the radius in this case? L. That's it. That's my answer. Simple. Once you know it, that's what I told you. Once you know it, it becomes simple. It's just if you don't know it, and we see if I show you this question, the first line, you will say, "Oh my God, this is very dangerous. It looks so difficult." If you know it, it's not difficult. Okay, let's do this one. A bulb of mass 0.5 kg is suspended from the end of a piece. So you have 0.5 kg. I'm just going to show mg, which is 0.5 times 9.81. The string is 0.5, so this is my radius. Vertical circle, constant rate of 120 revolutions per minute. So that is my omega, okay? Sometimes it is measured in revolutions also, but one revolution would be how many radians? One revolution is 360 degrees, so 2 pi radians. So 120 times 2 pi converted into radians, and this is per minute. I don't want per minute, I want per second, so divide by 60. All right, so that becomes 4 pi radians per second. I got my omega. Okay, what's the tension in the string? Okay, I'm also going to calculate V. V equals R omega. R is 0.45 times 4 pi, which is 0.45 times 0.9, 1.8. I'm not plugging the value of pi because that would introduce rounding errors, so I'm just leaving it pi. And then at the bottom it is T, tension is here, acceleration is towards. See why I'm doing, I could have just given you the equation here. It's just to help you internalize it. T minus mg. Always remember, resultant force is mass times acceleration. I want tension, ma plus, there is a lag, I don't know why it's lagging. Okay, now m is how much? 0.5 times v square over r plus 0.5 times 9.81. Okay, this is serious lagging here. Okay, now I'm going to just use your calculator. I'm going to use mine. So v square is going to give me 1.8 3.14 equal 52. Okay, if you're faster than me, that would be amazing. I'm really slow with the calculator here. Plus, that is around, okay, so I am getting my answer to be, which one? Okay, just give me a second figuring out, which is coming around 40 newtons. Okay, so that is this. So this is, now see, if you go to the previous one, this was just asking you the formula format. Now this is just testing your calculation skills. Not yours, your calculators. Your calculator is doing all the calculations, so let's not give you the credit. But it's just, kidding. It's just, you should be able to see the units, conversions, then remember the conversions, and then apply the equation. So it's just linking 2 or 3 pieces. So piece 1, piece 2, and then the piece 3. Okay, practice. Okay, let's do this one. I don't know why I have the answer written here, but let's just go ahead, pause it, and try to do it yourself. You've got the answer written here, try to get that answer now. So you have body of mass 0.5 kg fixed to one end of the string, rotated in a vertical circle. Okay, that's not bad. Radius 1.5 meters. Omega is 5 radians per second. Maximum tension. Now see, another point here. Maximum tension, remember, if the tension is to be maximum, it has to be at the point A, the lowest point, because the tension here has to balance the weight and it also has to provide the centripetal acceleration. So I'm writing T minus mg is mv square over r. So my T is mg. I'm hoping you've paused and done this. Okay, now my m is 0.5, 9.81 plus 0.5 times. Now my v is r omega. You can directly use this formula, m omega square r. I'm just not telling you unnecessary equations. Okay, times, so this is 15 5 is 75, so 7.5 whole squared divided by 1.5. Okay, so I'm assuming that's coming as 24 units. Be careful, these words are, till now I was just asking tension, now it's asking maximum tension. See, in this case it was telling you find the tension when it is at the bottom. Now it is testing your another skill, that you should know that the tension is maximum when it is at the bottom. Okay, let's do this one. This is, I think, testing going more further ahead. It bangs at an angle theta. Bangs means kind of bending. Okay, it's just like when a motorcyclist is taking a turn on a sharp turn, the cyclist ends up bending towards the center. So the same thing is happening with the aircraft. It's bending towards the center. Mass m travels at constant v, horizontal circular path of radius r. The lift force acts at an angle theta. So the lift force, if I find this component of the lift force, it would be cos theta. So I'm just taking this lift force as f. This will be f cos theta, and then perpendicular f sine theta. So my f cos theta is balancing mg, and f sine theta is providing the centripetal force. Now it's asking me tan theta, so I'm just dividing them. Cancel. Tan theta is centripetal acceleration divided by g. Centripetal acceleration is v square over r over g. So just v square over rg. R is small, so that would be my answer. What I've done here, I'm just explaining you that this is f and this angle is theta. So just made my right angle triangle. So this is the adjacent. Okay, so this would be cos, and this is the perpendicular. So because this is f sine, so this will also be f sine theta. Okay, if you are not very sure of this method, then you should be going back to the forces and getting this done. You should be able to break the forces into their components using the trigonometry. Okay, so that's it. That's the end of the circular motion. Keep practicing more and more questions. Merit Minds would be the place to go to. Thank you so much. Keep learning. Well done for doing this. Bye-bye.